These motion pictures, made through a microscope, show the domain structure of a crystal of iron being magnetized. The white lines, which are domain walls, have been made visible by the powder pattern technique originated by F. Bitter. Such patterns have been used by scientists in many laboratories in developing an understanding of magnetic hysteresis. In this film, we will discuss the theories that are fundamental to our understanding of hysteresis loops like this one, and show some of the experimental evidence which supports current theories. For example, we will discuss the coercive force Hc, which is the field required to reduce the induction to zero, and the saturation field, which is that field needed to make a sample essentially one large domain. The film will be divided into three parts. We will review the energies involved in domain formation. Then we will discuss a magnetically soft material, of which a typical example is transformer iron. And finally, we will treat briefly the magnetically hard materials that are used in permanent magnets. In the film strip, The Formation of Ferromagnetic Domains, four basic energies were discussed: the exchange, the magnetostatic, the magnetocrystalline anisotropy, and the magnetostrictive energies. In a ferromagnetic domain structure, these energies tend toward a minimum in the following way. The exchange energy is a minimum when all atomic dipole moments are parallel. The magnetostatic energy associated with an H field is a minimum when the integral of H squared dV over all space is a minimum. An H field is present whenever there is a discontinuity in the normal component of magnetization across a surface. The magnetocrystalline anisotropy energy is a minimum when the magnetization is along certain preferred directions called axes of easy magnetization. In the cubic structure of iron, there are three easy axes. The magnetostrictive energy in iron is a minimum when the material is allowed to change its dimensions along the magnetization axis. A wall separating domains also has its own minimum total energy, which is actually a combination of exchange and magnetocrystalline anisotropy energies. In a ferromagnetic domain structure, the sum of these four energies will always tend toward a minimum. The hysteresis loop for a soft magnetic material such as transformer iron is usually shaped like this. The width of the loop is generally determined by the coercive force. The loop is made up of an approximately rectangular area and two roughly triangular areas whose apexes are at the maximum induction plus Bm and minus Bm. The magnetization processes in these areas are basically different, and therefore we will discuss them separately, beginning with the rectangular area. When a field is applied to a specimen containing domains, the minimizing balance of the four basic energies is upset. The field tends to increase the magnetostatic contribution, and the other energies readjust to minimize the total energy. With this compass, we can demonstrate the effect of this added energy. If we hold the needle in this position and apply a field, the energy of the system is raised. The compass needle, when released, tends to align with the field because this action lowers the energy of the system. Now imagine what happens when we apply a field to this specimen. Because some of the magnetization vectors are not aligned with the field, the energy of the system is no longer a minimum. To lower the total energy, the magnetization vectors tend to align with the field, and the specimen may become saturated. But in an intricate domain structure, such changes are quite complicated. Therefore, we will study them with the aid of a simple case. Here is a drawing of a single domain with the magnetization along an easy axis. It represents a section of a larger specimen, which we will see later. Now, if we apply a weak magnetic field, which is not parallel to the direction of magnetization, the energy of the system is raised. However, unlike the compass needle, the magnetization may not rotate into a lower energy position. Rotation may not occur because this action would cause large discontinuities in the component of magnetization normal to the domain surfaces, and therefore would give rise to an H field. Thus, before the lower energy state could be reached, a large magnetostatic energy barrier would have to be overcome. Also, such rotation would be through axes of medium-hard magnetization. Consequently, an additional magnetocrystalline anisotropy energy barrier would have to be overcome to reach the lower energy state. However, the direction of magnetization does change in the following way. Let us put a 180-degree domain wall into the specimen. As its name implies, the moments within the wall rotate through 180 degrees. The wall has its own minimum energy per square centimeter regardless of its position. Thus, the wall can move without encountering either magnetostatic or magnetocrystalline anisotropy energy barriers. Consequently, if we apply even a weak field, the wall moves. One domain grows and the other shrinks because this lowers the energy of the system right from the start. In the laboratory, we can conduct an experiment to show wall motion, while at the same time we measure the resulting changes in magnetization. For this experiment, we use a single crystal of iron, cut in the shape of a hollow rectangle. This large model shows how the specimen was cut from a single crystal of iron. Each side may contain a single domain whose magnetization is along an easy axis. The magnetizations are at right angles, and the walls separating domains are called 90-degree walls. Actually, such a wall bisects the angle made by the magnetization vectors so that the components of magnetization normal to the wall are continuous across the wall. Thus, we have a flux loop that does not give rise to H fields. In the hollow rectangle, then, the exchange, the magnetocrystalline anisotropy, and the magnetostatic energies are nearly eliminated. And magnetostrictive energy is minimized as a result of the hollow configuration. Notice that a section of one of the domains is actually the simple case which we just discussed. As before, we can put in a 180-degree wall. Now the hollow rectangle has 8 domains with 2 opposing loops of magnetization. When the wall is in the middle of each side, the 2 loops cancel, and the crystal has no net magnetization. If we wind a wire around one side of the specimen, a current in the wire will generate a magnetic field parallel to 4 of the 8 domains. From a second winding, we can measure the changes in induction that are due to the applied field. Then, to see how the structure changes as the field is applied, we view a small area under the microscope. Here is the experimental setup. A special flux meter measures the applied field and the resulting induction simultaneously. This information is then automatically plotted on a recorder. Thus, the hysteresis loop will be drawn at the same time the crystal is observed through the microscope. Before starting, a colloidal suspension of iron oxide is dropped onto the crystal so that magnetic particles collect along the domain walls and make them visible. A cover glass is then added, and the experiment begins. The light line, which is the 180-degree domain wall, begins to move as the field is applied. Simultaneously, the recorder shows that the induction is changing. As the wall continues to move, the crystal approaches saturation. Before saturation is reached, we decrease the field to 0. However, the crystal retains its net magnetization. To reduce the magnetization, we reverse the direction of the field and increase its intensity. As a result, the wall now moves back toward its starting point. From this experiment, we can correlate the position of the wall with various values of induction. This plot of the data shows the relation between the wall position and the induction, or magnetization. As the wall, which we photographed on the surface of one side of the specimen, moved from the inside edge to the outside edge, the induction throughout the whole sample changed linearly from plus Bm to minus Bm. This plot is extremely significant because it proves that the walls observed in this way are not simply surface phenomena, but they show a body property of the material. From this and other data, we have developed the following explanation of the magnetization process in the hollow rectangle. Starting with an unmagnetized crystal, we apply a field in the clockwise direction. The 180-degree wall moves inward until it is pushed out of the specimen. The crystal now has only 4 domains, and the BH curve levels off, showing saturation. At this point, reducing the field to 0 has no effect on the domain structure, so we must apply a sufficient reversed field to create a new wall. This wall will nearly always nucleate and spread from an imperfection, such as a minute nick in the crystal surface. Once the wall is nucleated, it moves rapidly outward until the crystal again contains only 4 domains and is saturated. To change this structure, we must apply a sufficient field in the reverse direction to nucleate another new wall. This will usually happen at the same favorable imperfection as before. After nucleation, the wall again sweeps across the crystal, and the hysteresis loop is completed. This loop, which represents a real specimen, has an HC of about 1/100th Ørsted, or roughly 8/10 ampere turn per meter. Notice that this loop, which results from wall motion alone, is nearly rectangular right up to saturation. Here again is the loop for polycrystalline iron. This loop has a rectangular section, which we also attribute to domain wall motion. But to reach saturation, higher fields are required, so that 2 triangular areas are attached to the rectangular area. In the triangular areas, wall motion is not as important as a second process, which is called domain rotation. This latter process can be studied in the following way. This model shows how we can cut a crystal so that its sides are parallel to medium-hard axes of magnetization. The resulting specimen has a complicated domain structure that contains many domains. There are two opposing paths of magnetization separated by a zigzag 180-degree wall. Within each path, the many domains are separated from one another by 90-degree walls. Now, if we apply a weak field favoring one set of domains, the zigzag wall moves until the opposing domains are eliminated. The hysteresis loop resulting from such wall motion is quite rectangular. But notice that the magnetization has not yet reached saturation. This is because the moments are not yet parallel with the field, which is along a medium-hard axis of magnetization. Thus, we must increase the field substantially, on the order of 50,000 times, to overcome the magnetocrystalline anisotropy energy barrier. At saturation, the magnetization is parallel with the field, and the 90-degree walls are no longer present. Here, we see a small section of a single crystal which has been cut so that the zigzag wall results. Under a weak field, the zigzag wall moves slowly. One set of domains grows and the other set shrinks until the zigzag wall is eliminated from the specimen. Here is another section of a specimen from which the zigzag wall has been eliminated. Now, as a very high field is applied, we see complicated changes begin to take place. The sharply defined domain boundaries disappear as the magnetization within each domain rotates. Finally, we see that the specimen is saturated. The hysteresis loop for a crystal with a zigzag wall shows clearly the two separate magnetization processes. They are so separate that they must be plotted on different H scales, which we have indicated by the break in the abscissa. Wall motion, which is possible in fields of about 1/100th Ørsted, or roughly 8/10 ampere turn per meter, brings the magnetization to about 2/3 saturation. Then, to go the rest of the way, we must apply a field of about 500 Ørsteds, or nearly 40,000 ampere turns per meter. Notice that here, H and B increase and decrease along nearly the same line. The domain rotation process gives rise to little hysteresis. The energy supplied by the field in overcoming the crystal's anisotropy is mostly returned when the field is decreased, just as the energy stored in compressing a spring is returned when the compression is released. This means that the domain rotation process is largely reversible. On the other hand, wall motion in general is not reversible, and B lags behind H. The BH curve traces out the hysteresis loop whose area represents lost energy. There are several mechanisms that contribute to this hysteresis loss, two of which we will now discuss. First, look at this crystal, which is saturated and contains only 4 domains. To change the magnetization, we must create a 180-degree wall. Nucleating this wall takes energy from the field which cannot be recovered. Thus, nucleation of walls is one process which can contribute to the loss of energy in hysteresis. Next, look at this crystal which already has a wall in it. If we move the wall back and forth, but do not eliminate it, a minor hysteresis loop is traced. The area of this loop represents energy lost in overcoming impedances to the motion of domain walls, which are already nucleated. One important impedance is caused by any inhomogeneity in the material. An inhomogeneity usually consists of a non-magnetic inclusion, or sometimes a hole in the crystal structure. In either case, large discontinuities in magnetization are apt to be present along the surfaces of the inclusion, which are normal to the magnetization axis. Therefore, an H field and the associated magnetostatic energy may be present. In many cases, however, this energy is reduced by the formation of spike-shaped domains. In iron, the magnetizations within the spikes are at right angles to the surrounding magnetization, and the discontinuity at the surfaces of the inclusion is drastically reduced. The walls that form a spike domain tend toward the 45-degree angle that would bisect the right angle made by the magnetization vectors. Consequently, across the walls of a spike domain, the magnetization is nearly continuous. The H fields and resultant magnetostatic energy are therefore reduced to a minimum, although some fields remain around the tips. Thus, the sum of the magnetostatic and wall energies contributed by spike domains is less than the magnetostatic energy alone that would be present if spikes did not form. Now let us see what happens when a primary domain wall intersects such spikes. The spikes attach themselves to the wall and form a secondary domain structure that eliminates the magnetostatic energy which was concentrated at the tips of the spikes. This happens because the walls all make 45-degree angles with the magnetization vectors whose normal components are now nearly continuous across all the walls. But the walls of the secondary domain structure still have energy. Consequently, the walls tend to shrink until they have a minimum area. This is an equilibrium position for the structure. If we try to move the primary wall by applying a field, the secondary domain structure tends to cling to the primary wall to avoid the appearance of magnetostatic energy, and in doing so, impedes the wall's motion. To overcome this effect, the field must supply the energy needed to increase the area of the secondary domain walls. Here is such a secondary domain structure attached to a primary domain wall. If we apply a field and move the wall, the secondary domains cling to it and impede its motion. When we withdraw the field, the structure shrinks, and the secondary domain walls supply the energy needed to pull the primary wall back. If it happens slowly, the stretching and shrinking of secondary domain walls involves energy storage, but no permanent energy loss. However, under a steady field of sufficient magnitude, the secondary domains are stretched out until their wall areas have increased so much that a decrease in total energy is possible by the introduction of some magnetostatic energy. At this point, the primary domain wall breaks free, and the secondary domain walls shrink and close together. The resulting spikes stabilize, as before, with a minimum total wall and magnetostatic energy. Because of strains or other imperfections, a spike may swing around to a position of maximum stability. Here, as a steady field is applied, the secondary domain structure is stretched out to instability. Suddenly, one side breaks loose. A spike forms and snaps down to a stable position. Meanwhile, the other side of the structure continues to cling to the primary domain wall. Finally, however, it breaks loose and another spike forms and shrinks. Notice that even if the primary domain wall is moved very slowly, when a spike forms, energy is lost, which cannot be regained. Thus, this is an irreversible process. Now, the secondary structure no longer pulls back on the primary domain wall, so that if we withdraw the field, the wall tends to return only slightly. This happens because in any real situation, there will be many secondary structures attached to the primary wall at any one time. Some, like this one, will pull back on the wall. Others, such as this, will pull the wall forward. And still others, like this, will impede wall motion in either direction. Thus, when we apply and remove a field, we move the primary wall from one equilibrium position to another, losing energy in the process of disconnecting spikes from the wall. Motion in either direction from an equilibrium position will always be impeded. The wall will make large moves by breaking loose irreversibly from some inhomogeneities while becoming attached to others, thereby changing its equilibrium position. Energy is always lost in this process, and thus for large motions, B will always lag behind H. In cases, the distribution and size of inhomogeneities will be somewhat uneven. This causes the impedance to motion to vary with the wall position. When a substantial impedance is encountered, a large field is required to overcome it. Then, after the primary wall breaks loose, the field may send the wall shooting forward rapidly until another large impedance is met. Such jumps cause Barkhausen noise. We have discussed the principal processes involved in hysteresis in a magnetically soft material such as transformer iron. In general, the rectangular section of the loop is due to wall motion, which is the primary magnetization process. The thickness of this loop, as measured by the coercive force, is generally determined by the effects of several inhomogeneities, such as impurity inclusions and holes in the crystal structure, the nucleation of domain walls, and also strains in the material. In the high field regions of the loop, a process called domain rotation occurs. However, in polycrystalline materials, some wall motion is still possible in the high field region. This motion is impeded by the effects mentioned and accounts for the broadening at the tips so that a smooth loop results. In practical application, the DC loop of a soft magnetic material, such as silicon iron, may have a coercive force as low as about 1/10 Ørsted, or 8 ampere turns per meter. Silicon iron also has a comparatively high saturation induction of about 20,000 Gauss, or 2 Webers per square meter. When discussing wall motion, we did not consider alternating fields. In such fields, the hysteresis loop is generally fatter because walls encounter an additional irreversible impedance to motion, which is due to viscous damping. Eddy currents contribute importantly to viscous damping in metals. There are, however, other contributing mechanisms which are not yet completely understood. We will now discuss the magnetically hard materials whose loops characteristically show a very large coercive force. This loop for the permanent magnet material, alnico 5, shows a coercive force of the order of 600 oersteds, or nearly 50,000 ampere turns per meter, 6,000 times the coercive force of silicon iron transformer material. The loop also shows a large remnant induction, BR, in the neighborhood of 14,000 Gauss, or 1.4 Webers per square meter. This remnant induction is due to magnetization that remains after the field is reduced to zero. We call the section of the loop between BR and HC the demagnetization curve. The area under this demagnetization curve is a measure of how good the material will be in applications. Here are the demagnetization curves for two other modern permanent magnet materials, Ferromagnetic and bismuthol. Both of these materials have a lower remnant induction than alnico 5, but their coercive forces are higher, and the areas under the curves of all three materials are of the same order. Alnico 5, Ferromagnetic, and bismuthol are good permanent magnet materials because they are composed of fine particles whose dimensions are less than the thickness of a domain wall. Such a small particle has a minimum energy in the saturated condition, even though this gives rise to magnetostatic energy. The formation of smaller domains, which would decrease the magnetostatic energy, is impossible, because the creation of a very thin domain wall would be necessary. Such a wall would contribute so much exchange energy that the total energy of the particle is less when it is saturated. Therefore, to change the magnetization, we must rotate it through axes of medium-hard magnetization, and consequently overcome large magnetocrystalline anisotropy energy barriers. Now, if the particle is elongated along an easy axis, a change in magnetization gives rise to another large contribution to the energy. When the magnetization is along the long axis, the magnetostatic energy of the particle is a minimum. To change the magnetization by rotation, the field must overcome a very large magnetostatic energy barrier, which arises when the magnetization is along a short axis. Compacting such fine particles makes a good permanent magnet. Here is an electron micrograph which is representative of alnico 5. From study of such pictures, scientists now believe that alnico 5 is a non-magnetic matrix containing precipitated magnetic particles that have an elongated shape. In preparing the material, it is heat-treated in a magnetic field that is applied parallel to the direction in which the final magnet will be used. This treatment aligns the precipitated particles in the field direction and produces a significant increase in the magnetic quality of the alnico alloy. Today, much work is being done on both magnetically soft and magnetically hard materials. In this film, we have presented an elementary treatment of the magnetization processes which underlie hysteresis in ferromagnetic materials. In other types of magnetic materials, such as this sample of ferrite being studied at low temperatures, magnetization also takes place through the processes we have discussed. Thus, the basic ideas involved in domain wall motion, domain rotation, and the effects of inclusions are still valid.